The lecture is being recorded from now onwards. Sorry, I accidentally unshared it. Yeah, it should be shared again. Uh, for today's notes, I've come across over the weekend this pipe manual, and it also explains the section very well. It's a South African book, and it's published by the Concrete Manufacturers Association. But it'll only deal with concrete pipes, which is a specific type of pipe, which we could regard as a rigid pipe. But it'll give you a good understanding of the loads that are applied on the on pipes. So when you dig a trench and you put the pipe into the ground. So what will be the loads that are transferred to the pipe? It has an excellent discussion on that, but like I mentioned, it's restricted to what we refer to as rigid pipes. I'll explain the difference to you between a flexible pipe and a rigid pipe. Uh, and so a concrete pipe is regarded as a rigid pipe, and it's in that context that these notes are written. Then I'll go on to explain to you about the external loads on pipes and the types of loads that are applied to pipes, and how do we determine the actual load that is being transferred to the pipe itself. So for that, this set of notes that you have, it's written. It's just I've extracted this a few pages. The author is Stephenson. Uh, who's a renowned author with regard to water, the design of pipelines. So this is a small extract from there, but it's very well explained in these sets of notes. I know it looks old-fashioned, whatever, but it's still very well explained. So I'll go through these notes here, and these notes also cover the discussion or the formulas for a rigid pipe also. Then there's another set of notes. This one also is taken from a book in the library, which explains to you the Marsden theory for flexible pipes and for rigid pipes. And then you'll understand the difference between a flexible pipe and a rigid pipe, what's going on in there. The last set of notes, this I'll cover in Wednesday's lecture. And this will be with regard to pipe materials and corrosion in pipelines, and that will bring an end to the syllabus for this particular semester. So that's just an outline of what we're going to do. When it comes to the pipe, with regard to the loads on pipelines, okay, so find the relevant section here. Just bear with me. Page 16. So we'll go to the section on this, page 16. I will upload this. It's available for free, so I'll upload it for you onto Moodle. It's not currently on Moodle, but I'll upload it for you, and I'll strongly advise you to read through this. Um, so what are the loads on buried pipeline? Now you notice the term there, buried pipelines. So if you're applying a load directly onto a pipeline, the pipeline is not buried, and you're applying a load direct, well, then you know what load you're applying to the pipeline. Right? But if the pipeline is buried and you now apply a load on the surface somewhere, what is the load that's actually on the pipeline itself? So that's what we're looking at in this particular section over here. Right. Now, every buried pipeline will be subjected to loads that and those loads will cause stresses in those pipe walls. And it's easy to work out what the strength of a pipe is as a circular section, and that's from your mechanics of materials. You'll be able to determine what the strength of that pipeline is, and then you can compare it to the from once you know the loads that apply to the pipeline, you can work out what the stress in the pipeline and see is the pipe strong enough for that. Right. So the loads, we generally will broadly define them as either primary loads or secondary loads. Okay, let's enlarge this here. Right. So the primary loads, these are the main loads that apply onto a pipeline. So not main loads, but these are when you say primary, these are loads that you directly apply onto a pipeline. Secondary ones, they arise out of the conditions in which the pipe is bedded. Depending on the conditions around the pipe, will create loads in the pipe. So that's what we're referring to secondary loads. The primary loads are the pipe is buried, so the mass of the earth above the pipeline is going to apply a load on the pipe. Uh, you may, if the pipe goes under a road, or even if it's within a stand or somewhere, and it's possible to get traffic loading, that if vehicular traffic drive over the ground under which the pipe is buried, so you can get traffic loading. And then the internal pressure loading. We're dealing with water pipelines, and we know that we have residual pressures and static pressures within the pipeline. So these are obvious loads that the pipe will have to withstand, or the pipe must be strong enough to be able to withstand these. Every pipe in its normal operating conditions will have to bear these loads, or will have to withstand these loads. Right? So we refer to these as the primary loads. The secondary loads, these are uh, arising out of the circumstances around or due to the environment around the pipeline. And for example, there may be, for example, if the pipe is bedded in a clay soil, from your geotechnical engineering, you know that you get consolidation, settlement in the clay. Clay also, depending on the moisture content, it may absorb water, or it may, from time to time, or the water may dry out and then it shrinks. So you get these movements in the ground, and that would create loads in the pipeline. That would result in a loading on the pipeline due to the changes in the moisture content. Right? So that again, that's now because of the environment around that pipe. You could get, for example, tree roots or foundation and bedding. So when they say behaving unexpectedly, suddenly you get settlement of a foundation, and then loads start being transferred to the pipeline, or maybe tilting of a building or something like that. Embankment conditions, elongation, thermal conditions. You may get due to the change in seasonal temperatures, or you may get snow conditions, for example. So these are all loads that we may not have foreseen that may arise within the pipeline itself. So we refer to these as secondary loads in the pipeline. But when we're designing, we're checking the pipe for now. In this particular model, we're looking primarily at primary loads on the pipeline. Right. You see at the last note, it says here that the secondary loads, you can take contingency measures in the design so that you could eliminate those loads from the pipeline. It is possible to mitigate against those in your design so that you would eliminate those secondary loads. Right, so with regard to the loads on the pipeline, the first one we said was the primary loads. You notice was the mass of the earth fill above the pipe, and this is what we'll be concentrating on in this particular module for now. Traffic loading, you would know the kind of vehicular traffic you're expecting to drive over the buried pipeline, so that you would be able to determine what the loading is. But the loading that the mass of the earth fill above the pipeline, this is what we will concentrate in this particular model. The internal pressure that will come out from your hydraulic design, and that's where you would determine what's the internal pressure in the pipeline, and then there are simple formulas to check the stress in the pipe, and then you compare it against what the allowable stress, depending on the material that's being used for that particular pipeline. Right, so well, of course, we insisted in this first item for this particular module. That's where all our efforts will be directed towards this first one. The mass of earth fill above the pipeline. What load will that transfer in the pipeline? But now, this is this particular catalog is based for concrete pipes, and they've got tables and things. So I'm not going to worry on that. I'm more looking at the actual understanding the concept of the loads that you would have transferred on the pipe. So when it comes to the earth loading, to calculate the earth load on a buried pipe, or they refer to it as a conduit, that's because it's not necessarily restricted to a round pipe. The loading here could be to any, you may have a culvert or a rectangular culvert, or any other kind of other shaped pipe. So you could apply the same procedure for that also. So that's why they just refer to it as a buried conduit. Right. Now, to establish what are the factors that would affect that would determine the load on the pipe, the installation method, the fill height, that's pretty obvious, that the fill height, the backfill density. So you can see the soil conditions, right, and the trench width or external conduit width. Now, this is an important part in the design, the trench width and the external conduit width, and we'll talk about this. You'll see when we refer to flexible pipes and rigid pipes and trench conditions or embankment conditions, especially trench conditions, embankment conditions. That's where this part of the design, that's where these factors will have an influence, the trench width. So we differentiate between two conditions. The one is a trench condition and embankment condition. Now, broadly speaking, what's the difference? Why would you get different design values, or what makes such a big difference with regard to whether it's a trench condition or an embankment condition? Now, in a trench condition, if you look, for example, uh, okay, let's, for example, look at diagram B. You have a pipe like that in the ground. Right? So in diagram B, we're looking at this diagram B here. Right? So we have dug a trench like this in the ground, and we've placed a pipe like that in the ground. And then let's say, so you just have the pipe in the ground like this over here. Right? So you haven't backfilled or anything like that. So it's just the pipe resting on the ground like that. There is no load on the pipe itself like that. Right? Nothing is being applied to the pipe like that. So it's not carrying any weight above that like that. If you were to apply, then backfill this pipe like that with soil above this, so you now have the backfill soil may not be exactly the same soil uh, as the soil that's in the ground. When I say not exactly the same, you may have excavated, piled up the soil on the side, and then put it back. But just bear in mind that in doing that, in excavating and placing it back, you have disturbed the soil. It's now in a different state. It's in a loose state. It's been mixed up. It might have had a profile in the ground, may have been a residual soil, and it may have been had maybe more sandy on the top and more stony towards the bottom. You've now excavated all of that and you've mixed it up. So it's now a different soil. When you put it back, it's not the same as the soil around it over there, right? The undisturbed soil adjacent to the trench. So you now backfill that soil. If we assume that there is no friction, for whatever reason, if we made the assumption that there was no sidewall friction, so we've got this prism of soil that we've backfilled above the pipe. And if we assume that there's no friction whatsoever between this backfilled soil prism and the existing or adjacent uh, soil adjacent to the trench, then the full weight of that prism of soil will have to be borne by this pipe over here. So this pipe, the earth load on this pipe will in essence be the weight of the soil above it. Right? This prism of soil, if you have to take whatever the shape is, you allow for that curved shape at the bottom. And if you determine what the weight of that soil is over there, so obviously the deeper the trench, then the larger would be the load, because the weight of this entire prism is being supported by the pipe over there. So that would be the load on the pipe, assuming that you had a frictionless trench. So the sides walls of the trench are frictionless. Now, let's say we do have friction. Well, let's say, so this is the one condition that we have over here. Right? Uh, Also, in this, looking at this particular one, in this particular case, for example, also, uh, if even if there was friction, if it were if we assume that they would be friction between the earth fill, the backfill, and the side walls, uh, if the pipe is rigid, like let's say this pipe is very rigid, it does not yield at all. So this soil has nowhere to go. You're not going to get settlement. Right? So for friction to develop, you would first require some movement of the soil, some settlement of the soil. So this pipe would be carrying this full load of soil away, because the soil cannot move in whatever way like that. It's just resting on the pipe like that. Okay, let's take the second situation that we have here, where we now have a pipe like this, and you see that the trench is wider than the pipe like that. We've dug a trench slightly wider than the pipe. We've placed the pipe in there. We might have put some special soil at the bottom there. We refer to that as the bedding, the pipe bedding at the bottom underneath the pipe. We wouldn't want to we wouldn't want to lay the pipe on stony material. It may damage the pipe. So we want a bedding material that would exert a uniform pressure on the pipe and without damaging the pipe. So we've put a special bedding. We've selected what we call selected soil at the bottom underneath the pipe, and that would be the bedding of the pipe. We then come in back for the pipe over here. Uh, Now, what will happen with regard to the loading of here? This is for a rigid pipe, right? This particular catalog is for a concrete pipe, so it's a rigid pipe. The the soil above the pipe would be held back, right? It cannot move down. If you took that prism of soil above the pipe like that, at that point, that prism of soil cannot actually move down. But adjacent to the pipe over here, this soil over here, it's a loose. You put it back in the trench loose, and it can actually move downwards. It'll settle, so you'll get some settlement occurring above this pipe over here. Right? So what will happen is, for example, the ground might eventually, after a while, look something like this over here. Like that. So above the pipe, you get less settlement because of the rigidity of the pipe. But on the sides of the pipe, the soil can settle more on the sides there. So you'll get this movement. So the soil moves downwards like that on the sides, along the side walls of the trench. So because you've got that movement down on the side walls of the trench, you get friction acting uh, between the sidewall and this prism. So if the sidewall wants to move down, then the frictional force on the sides, so the adjacent earth will apply a force upwards like that. It will help, in other words, it will help to hold up. Friction will help to take up some of the load of the soil prism like that. Right. So the actual load transferred to the pipe would be less than, for example, the right-hand case, where the entire weight of the soil prism is carried by the pipe itself. Here, some of the soil prism, some of the weight of the soil prism is carried by the side wall of the trench itself due to the friction that you have there. So the net load on the pipe will be reduced because of that effect also, because of that effect that you'll have there. So so you will see that friction becomes important, is an important factor uh, in terms of the loading that would be applied to the pipe. Then another situation can arise. We may have a pipe. We may put it in a very shallow trench, or we may be laying it on the surface of the ground, or even as you see over here, that's the bottom line over here that you're seeing here. That's the natural ground level over there. So we may have dug a very shallow trench, and part of the pipe is above ground, and we then come and backfill around the pipe itself, or above the pipe. So we've built up an embankment, right, to cover the pipe. We don't want the pipe exposed, so we will then come and we've covered it with soil like this. So under these circumstances, what would happen is the soil directly above the pipe would carry that load. It would resist. It has to carry that weight of the prism above the load. But then, because the side that's so the soil that's adjacent to that prism over here, this soil here can settle because the ground over here is not rigid. Right, so there'll be a settlement that will be taking place like that. Uh, so this is an embankment right through. So this soil all around here can in time will settle down as it compacts like that. So you get rain or whatever like that, and the soil particles will get lubricated, and you can then get settlement of this pipe, or even vehicular traffic, or just under normal circumstances in time, this will settle down like that. Right? For example, when the municipality digs up a trench on the road, when they do repairs, and then they backfill it, and then you see that it settles. So even these guys who come and lay the fiber cables, they dig a trench, and in time, where they've dug, you actually see that settlement taking place there. So you'll get settlement over here along adjacent there. But above this, you cannot get settlement because this soil cannot move. The pipe is rigid. The pipe does not give. So because of this, so the soil on the right-hand side and on the left-hand side of the prism is moving downwards. So it'll apply a drag force on the prism. It's actually going to increase the load on the pipe. Due to friction, right? The friction between the side wall and that, you're going to get this dragging force, like what you see, those arrows are drawn. So there's a drag force downwards. So it actually increases the load on the pipe. So this pipe will be even worse off than this, the load of the soil prism above it. Besides carrying the weight of the soil prism above it, it's also carrying some of the load of the soil that's next to the prism, because that soil wants to settle, but now you have friction between the two, the prism above the pipe and the natural of the soil away from that prism, and you then get this downward drag force on the pipe. Right, so it'll be under a worse condition, and we refer to this as embankment condition. We call this an embankment condition. Right, and we'll see you'll come across formulas for determining the load when you have an embankment condition. Now, now, in an embankment condition, there are three circumstances that can arise in an embankment condition. The one is you've got the natural ground like that, and the pipe is totally above like that. So we refer to this as a positive projection. The pipe is totally above, and you'll come across the terms in these notes: positive projection and negative projection. Another circumstance that can arise is like the one that you see where the pipe is partially above and partially below the ground level like that. But you still have a positive projection of that. The third situation can arise is where you've dug a very wide trench. For example, you may have dug a trench like that, a very very wide trench like that, and you've now put the pipe uh, sorry. Uh, you've now put the pipe in the ground like that, something like this. Let's say, sorry, I don't know why my mouse is not drawing. Okay, the mouse is drawn. So the pipe is actually below ground level, but because of the width of the trench over here, uh, the friction forces that you develop on the side here will have no effect on this. It's too far out over there for that prism. Because of the width of this soil prism at this point over here, or because of the width of the soil prism, you'll still get embankment conditions developing. Let's say if that's your backed full like that over there, you will still get embankment conditions. So I've drawn this wrong here. Just bear with me. Uh, you'll backfill here, right? So you'll backfill at this point. Yes, you bring it back to natural ground, but because of the width of this fill soil that you have here, it's so wide that in effect you will this soil over here will still want to settle on this side, and this soil here can still settle over there. That friction that you're developing over there will make no difference, and you'll still get the soil prism here and soil prism, and you'll still get the drag force happening down there. So you still have an embankment condition over here, even though it's in a trench, but it's a very wide trench. So for the for embankment condition, there's these three situations that can arise, and there are formulas for determining the loads on the pipe ladder. Right, so you can see the width of the trench will play an important role in determining the load that would be applied to a pipe. Right. Then the notes, this particular set of notes goes on here, and they give you the formula for calculating the load on the pipe, and you can see that it's in kilonewton per meter. Right? So that's kilonewton per meter on the pipe. All of that. So that's the formula that you'll see over here. Now, if we study this formula in a little bit more detail, so what are these variables that are in this formula? What's determining the load over here? The derivation of this particular formula, I've got a set of notes here that will assist you. So this set of notes that you see here, this is on Moodle by Marston, and the derivation of that formula you see under the section here, external loads in this section here. So if you go through it, there's the calculation for all of those for that, and eventually you'll see it will simplify. The calculations simplify through that particular formula. So there's the formula here. This is the diagram that's used for the derivation. The frictional forces as the weight of the soil, as you go further, sorry, as you go deeper into the ground to the pipe, the weight of the soil above increases. So you'll realize more friction on the side like that. So the frictional force is least on the top, but larger as you go down. So that's why they've taken the differential over here at this point. Right. So, and then they integrate it over the height of it like that. And that's what's being done in this. And you can read through the derivation of it, and you see we come up with that formula there. And then you see there's this C there's a this value for CD, and the formula for CD is given to you over here. And then there's also graphs to assist you in calculating or in determining what that value for CD is. So coming back to this particular pipe over here, you see that's the exact, let me just go back here. You can see CD gamma BD squared over there. Right? So exactly the same formula over here. The C, the W, and the W is the gamma. The unit load of the fill material, right? The soil that you're filling, backfilling, that's the unit weight of the soil. And you'll be familiar with that from geotechnical engineering. We use that symbol gamma for the unit weight of soil. The BD in this formula, you can see in the diagram here, that's the trench width, the BD that you have here. So that's the BD that's in that particular formula. You're going to square it. And then that value for CD, and the formula for CD is given. And thereafter, you're given a graph to assist you in calculating the value for CD or reading of the value for CD. You can use this graph and read off the value for CD from this graph over here. There. Uh, so it's coming back to this particular one over here. So the value for it's referred, they call it CT, the trench, because you have trench conditions. So they're referring to it as CT in this particular formula here. And they give you a graph. So there's tables here for the calculation of all of this. So let's go here. And talk about that with the value for CT in this particular one. Just bear with me. I just want to say, I've lost my train of thought here. Oh. Just bear with me. I've just found this book today. I'm just trying to find where they give you the value for the C, the CT and the CE for different. The CE is for embankment conditions, and the CT is for trench conditions. Right? So so there is a graph here that you read it off with. Okay, so maybe it will be further down. Just bear with me. So to find that, I did see the graph for it somewhere here. External loads, internal pressure. No, I think I've passed it somewhere. No, it's not in here. Just bear with me. Okay, wait, we'll come across it just now. I'll find the C value that you want. You can also read it off from the set of notes that I've given. But I know the set of notes is complete, so it is. Maybe I've passed it earlier. The value for this, maybe it's a little above this. There is a. This is the hydraulics of the pipes. It won't be there. So just bear with me. I'm just trying to look. And definitely is somewhere here, the way they give you the coefficients for that over here. Right? Trench with certain stairs, the trench. My apologies for this. I'm just need to locate it for you. The C value. Okay, I don't want to waste time. I'll look for it and I'll let you know where it is on that in this particular document. If you look at this particular document that you see here, that's the same value over here. Right? The C here it's referred to as CD. In that diagram that I was going to, they used C for CT for trench conditions and C. E for embankment conditions, right? So it's a different C value for depending whether you got embankment conditions or whether you got trench conditions. So that's where you got a difference in the formula for that. Now, for this particular one, for the trench, for rigid pipe and trench conditions, the value of that C, D, this is the graph that you would use. And again, it takes a bit of a while to read off. If you notice in this formula here, you've got this value here, KU H over B like that. So you got to read, you can calculate that value and you'll come with a different, there's a discussion on that for the different, if you simplify that formula and you come up with that, you can read it off further. So based on that, for the different key KU values, that part of the formula, depending on what value you would get over there. And based on that, you can then this thing read off from this particular pipeline over here. The explanation of this particular formula also, there is, I just want to go back here and show you, they do have a discussion here on that for those values. About this, depending on what type of soil you have, there is somewhere here that they talk of the discussion for those values of the. Okay, I don't waste time on that, but you can. This is you use this graph over here that you see, figure 2.2, and you would be able to read off the C value for that and plug it into the formula, and that's the unit weight of soil, and then the B is the trench width over there, and that would determine the load that would be transferred onto the pipe over there in kilonewton per meter. Right, so fairly simple. There's an example here, so you can see how it's applied. I know it's in imperial units, but you'll still be able to follow it. It's more just understanding the use of the formula, so you can read it off from here, and you can. There's an example, and you'd understand it from there. Right, so this is for the case of a rigid pipe and under trench conditions. Then the next discussion would come, okay, under uh, embankment conditions, where you have embankment conditions. Now, I explain to you about the embankment conditions, and I'll come back to that particular diagram, to this particular discussion in this particular book of it. So, we've spoken about trench conditions for a rigid pipe over here. You can read through these particular the notes that are given you, the loads on the conduit for given trench widths. Right? So these are for standard trench widths that, because this is for a particular type of pipe, and concrete pipes, they come in 6 sizes. The trench widths are normally determined by depending on the diameter of the pipe. So it's already worked out for you in the table what would be the loads on the pipe over here. Right, so it's given to you. You can just read it off directly from this table for a particular width over here. For embankment conditions, again, then in this particular set of notes, you'll see that, let me just enlarge it, the same kind of formula like we had previously, but this time we got the CE for embankment. The W is still the same, the unit weight of the soil, right, in kilonewton per meter cube. So the unit weight of the soil, that's the W. The BC, that's the previously the B. Okay, let me just go back here. We had the width of the pipe, right, BT. That was the trench. Right, so the trench width of the pipe over here, that you see trench width of the pipe for that trench conditions. Under embankment conditions, we have BC in the formula, and here it's the diameter of the pipe. Right? So that's the difference in the formula. Just make a note of that over here. Right? So under embankment conditions, we're dealing with the width of the pipe, because remember, on the embankment we said we have it's very wide, so we don't the width of the trench is immaterial. Right? The fill behind it is the backfill behind it is quite broad, and you're now going to get this drag condition on the prism above the pipe. So it's the diameter of the pipe that's the more important that will control it. Right, so that's what we have, and then we have this the coefficient CE in this formula. Then, and again, for this coefficient, there's a table that you can look up. And if you come to this set of notes over here, when it talks of embankment conditions, again, you'll find that in this figure 2.3, you'll be able to look up the value of that coefficient in this particular table here. You can use it. The formula is also given to you. So I'm looking at the long one there. The coefficient is in figure 2.5. And that's the value of the coefficient that we have for embankment conditions. So you can read it off from this particular table here. It does take a while to follow to be able to read off from this table. I'll leave it to you. You can spend some time and learn how to read off those tables. But that's sometimes the derivation of the formula also you'll see from that over there. Like the formula itself that's given to you in this. So where's the derivation? Okay, yeah, that's the formula that we have here for embankment conditions over here. So that's the embankment condition. Very similar again, you see, and that's the BC. The BC, you can see here, that's the BC, that's the pipe diameter in that particular formula there, right? So that's the same thing that we have like in that other book over here. So to determine the load, you've got the formula, and then you can look up the coefficients, the C for the embankment conditions. That's the figure you use. Plug it in, and you can determine the load on the pipe ladder, the soil load due to the soil prism on the pipe ladder. Right. So this is all for rigid pipes. The discussion was for when we have a rigid pipe. Now you can read again through the rest of this notes. It's informative, all the theory. The next section will be to understand is the difference between flexible pipe and rigid pipe, and then you see that there's a modification to the formula for the load transfer to a flexible pipe. Now, it's interesting to read through this particular section about a flexible pipe. Uh, Before I get to flexible pipes, I just want to finish off this particular set of notes on the uh, rigid pipe. Right, so we spoke about the embankment condition, and this is just now I tried drawing a diagram with regard to the embankment installation, and I spoke about positive projection, where the pipe level is, where the top of the pipe coincides with ground level like that. That's referred to as a zero projection. Right? So zero projection, and a negative projection is where you have a very wide trench. Okay, this diagram is a bit misleading, but you have a very wide trench, and the pipe, the top of the pipe is below the ground level. The embankment, because you need a certain minimum cover above the pipe to protect the pipe, so that's where the ground level or the embankment is over there. So we've backfilled to that top level over there. So now the pipe is completely covered like that. So in all of these, we're backfilling to the top like that at that point over there. So this diagram will help you understand the difference between a positive projection, zero projection, and a negative projection. And it does come into play in some of the formulas that we'll see further down over here. Right. So the various embankment conditions are illustrated away. In a test or exam condition, you should be able to differentiate between these three, or you should know what the difference is between the different types of embankment installations and things like that. You can read through all of this. In terms of the load transfer, there you'll see the explanatory about how the friction, this thing that. So yeah, you'll find it informative just to read through the rest of it. The traffic loading, that's not a part of the our it's something you can read off. In practice, you will need to know that if your pipe is under a road, and you can always come back and read up to that. And there's an interesting discussion over here to explain to you about the traffic loading on a pipe, but it's not within the scope of this particular module. So I'm not going to spend time on this section here any further. So the next section we'll continue with is the load on the earth load or the soil load on a flexible pipe. Now, what's the difference between a rigid pipe and a flexible pipe, or what's all this fuss about rigid pipe and flexible pipe over here? Now, uh, rigid pipes generally are concrete pipes or vitreous clay pipes. Vitreous clay pipes, you won't see them being used anymore. They were used many, many years ago, maybe 50 years ago. They were prevalent. They're made from clay, but now they're too expensive, so they're not used anymore. So concrete pipes and what we call also fiber cement pipes are generally the rigid pipes. They're also brittle materials, right? Those particular pipes, and it's the brittleness that results in them being classified as rigid pipes. But what is and what do we mean when we talk about a flexible pipe? When we say that a pipe is flexible or something. Right. So there's an interesting discussion here, and I'll advise you to read through the discussion over here. In simple terms, before I get to the actual explain to you what's the difference between a rigid pipe and a flexible pipe. Uh, if you look at this diagram, and I'm just going to explain a bit before I explain what's going on in this particular diagram over here. If we look at it, we have the soil prism above the pipe like that over here. Right? So we have a soil prism above the pipe over here like that. And for the rigid pipe, we said that, well, okay, the soil settles and then you get friction on the sides over here like that. But this pipe is, by its definition, it's rigid. So it stands its ground and it doesn't give anyway. So it's not deforming like what we see in this particular pipe, in this particular diagram. So a rigid pipe, uh, a rigid pipe, by definition, right, what's the difference between a rigid pipe and a flexible pipe? A flexible pipe can undergo a deflection of 2% or more without any, without any duress. Right. So without suffering any detrimental condition, or without its strength being weakened, or without it being cracked in any way or whatever. So a flexible pipe can withstand a deflection of 2%. So you apply a load like what you see over here, and it'll have undergo some deflection like what you see over here of 2%, and it's fine. It doesn't matter. But a rigid pipe, you have to apply a load to it, and once you experience about 2% deflection, you then the pipe will start developing cracks, or it starts undergoing duress. It's under duress. Right? So that's the differentiation between a flexible pipe and a rigid pipe. So a rigid pipe will will undergo quite large deflections without losing strength in any way, or losing its intactness in any way. It's still without cracking or whatever like that. Generally, flexible pipes are steel pipes, and your plastic pipes, your UPVC pipes, your HDPE pipes are generally regarded as flexible pipes. So let's look at what happens, how the load transfer mechanism happens when it comes to these flexible pipes. So when you apply a load like this, because this pipe is flexible, you'll apply the load, and after beyond a certain load, this pipe will just deflect. Right? You're applying a larger beyond a certain point. The soil load from the prism is large enough. It will deflect with this pipe like that. So the pipe will undergo deflection. It will bend. When it bends sideways, it then pushes on the side over here. So you get support from the side. The soil on the side here is now providing a support to that pipe over there like that. Right? And if you increase the load, well, obviously it'll deflect a bit more, and you get a bit more support from the side like that. And you also get support from beneath the ground over here. So you got you can see that the side fill over here is contributing towards this, towards resisting that load that's being applied to the pipe like that. For a rigid pipe, it's only the pipe itself. The side fill, the soil on the side is not actually contributing towards resisting this load that's being applied to the pipe. The pipe is stiff. The pipe just stands up. It's like a strong person, whatever, and just wants to take all the load by itself on the top. Right. So that's the difference between a rigid pipe and the flexible pipe. Now, you can read through this set of notes here, and they talk about how the discussion about this uh, with regard to flexible pipes, whatever. A, a test was done. For example, they say at Utah University that they did tests with regard to rigid pipes and flexible pipes. So rigid pipe would usually be a concrete pipe, whatever like that. And they applied a load of 3,000 pounds per foot on a buried pipe like that. And at that point, the pipe started to fail. It developed fractures at it, whatever, right? So this was for a rigid pipe. But under the same soil conditions and the loading, they put a PVC pipe like that, and it deflected 5%, right, with that particular loading. Now, the rigid pipe, when it start developing those wall fracture, that would have been at around 2% deflection. So it would have only been about 2%. It would have only deflected about 2%, and by that point, it would have shown signs of distress, and the wall fracture and things would have started developing with the load of that 5,000 pound per foot. But when they applied the same load to that PVC pipe, it deflected 5%, showed no distress or whatever like that, no fracture, anything occurred like that, and it was still fine at that point over there. And it would actually fail at a load of 4 times that amount before they suffered any noticeable distress. So it could withstand a load of 4 times that amount over there. Right? Yet it's a weaker material. The plastic pipe generally is a less stiff than a concrete pipe, or one would regard it as a weaker material. But it was able to the factor of safety. So this is the point at which it was the failure load was 4 times greater than that for the concrete pipe. Because it was, and the simple reason was because it's a flexible pipe. And the reason behind it is, like I explained, it can, as I mean, you had that 5% deflection, but then so the pipe flattens out slightly. It takes on an elliptical shape, but it will not it will not flatten out like this. It doesn't flatten out completely because you get the soil from the sides over here help to hold it in place like that. So now something's gone wrong here. Lost connectivity. No, what's happened? No internet. Maybe my data is finished. Okay, are we back? Okay, I don't know what happened. I think it might be related to load shedding. For some reason, I think the internet connection broke off again, and I see now it's connected again. So I may just confirm, are we back live again? Do you still see the PDF file on the screen?
Yes, sir.
Okay, okay. My apologies for that. Okay, so the, the long and short of it, to come back to it again. So we have for flexible pipe, we will have a different formula for load conditions. Flexible pipe will be able to withstand much larger loads compared to a rigid pipe. And the formula for flexible pipe, you see that's in the notes over here. It will not be in those other notes because that's for concrete pipe, which is a rigid pipe. Right? So flexible pipe, we see similar kind of formula, but we've got an extra term over here. Here you can now see the BC, the diameter of the pipe also being coming into this particular formula over here. Right, so you got the trench width plus the diameter of the pipe. You're multiplying it by the diameter of the pipe over here in this particular formula over here. Right. So and the value for CD, you can see is the same from that figure 2.2, the unit weight of the soil, the BC and the BD over here. That BD, the trench width, you can see BD, that's trench width, and BC is the overall diameter of the pipe over here. And that CD, that's from the original figure 2. It tells you over here from figure 2.2. If we go back to that original graph for the first one that we had here, this was CD was the first one, figure 2.2. So this particular graph over here. So you read off the value of CD from this particular graph over here. And that will give you the load that's being transferred to that particular pipe for the flexible pipe over here. And so that's the formula that we have for the flexible pipe. The rest of this is just a discussion to explain to you the mechanism. I leave it to you to read. It's interesting to understand it. If you imagine, for example, the pipe as a spring, but the soil above next on the either side is a softer spring. So the pipe will be resisting some load. It will undergo some deflection, but the springs on either side also help to carry some of that soil load that's there. And that's the explanation that's been given here. You can see flexible spring. The pipe itself is a stiff spring. The soil on the side of the pipe is a flexible spring. That's the example. That's what it's been likened to. So those are the three springs over here. The pipe is the middle flexible spring, and then the sides over there. And then depending on whether the type of soil, whether you got stiff or what type of soil on the side, or whether the pipe itself is flexible or stiff material under those conditions. So read through those explanations and you'll come across this formula, and even the derivation of that formula is given to you down here. So yeah, the time's almost up, so I'm not going to spend much more time there. So for the trench conditions, that's the formula that we have. So the trench condition, and then for embankment condition also, you'll see for the flexible pipe, the formula is given to you for embankment conditions. And the previous one was for trench condition that we had over here. There's the trench condition, the same formula. The Marston formula for trench conditions, and then the Marston formula for embankment conditions. You can see here it's just the diameter of the pipe. The trench with embankment condition, because it's large, it spreads out, so that the width of the embankment does not come into the formula there. Same like the previous for rigid pipe ladder. Right, and you look up that value of CC over here also in this particular formula. Then it goes on about tunnel loadings. It's interesting if you want to read it, but it's not within the scope of this particular formula of this particular module. So I'm not going to delve further in. I've just left it in out of interest for you at a later point. If you want to read through it, you can read through the material that's down here for culverts or tunnel conditions. It's also interesting reading, and I've just left it in for you. Okay, with that, I'll end the discussion on this section on flexible pipes and rigid pipes and trench conditions and embankment conditions and determining the loading on those pipes. There are examples here. You can read through those examples and see how they work through, and you'll get a really good idea of how it's done. Right. So, yeah. Okay. Any questions? Anybody? Any queries? Any
Yes,
questions?
sir.
Yes, you can go ahead.
Regarding the exam condition, so is this our last class or we still gonna have another one on Wednesday?
No, I will. Wednesdays will be, you'll have to come to campus because you have to hand in your assignment. And I'll have a short discussion about corrosion in pipes. That we haven't covered the section on corrosion of pipes. So I will cover the section on pipe materials and corrosion of pipes. It's a section that you could easily read through. You don't really need much input from me for that, but I will quickly go to that. The section is this. So it's going to show you for that one, this particular set of notes, which is on Moodle for you. And I will cover it from there. It's very well explained in these sets of notes over here, the pipe materials and with regard to corrosion for the different pipe materials, what type of corrosion they undergo and what are the factors that lead to their corrosion. That's so it's all in this particular one. And I'll quickly go to it in Wednesday's lecture. But Wednesday's lecture will not be online. It will not be on Teams. Wednesday's lecture will be on campus in the venue. Look at your timetable, whatever the venue has been allocated, and it will be there.
Okay.
Any other queries? Hopefully you have made good progress with your assignment. You should be almost complete by now. You have to hand it in on Wednesday at the venue there, right?
Yes, yes, sir.
Excuse me, sir. I have a question regarding the assignment.
Yes, you can go ahead. You had a question on?
Yes, I just want to double check with terms of contours. When we need to find the ground level for a manhole, we inspect like how you did for the examples that you did for us.
Sorry, just repeat that question. I'm not following it clear. When you need to find the ground level for
a manhole,
yes,
we inspect like how you did in your examples that you did for us.
yes, you've got contours, right? You have the layout plan, and you've got contours on the layout plan. So you'll have to interpolate between those contours.
Oh, so we interpolate.
Yes, you'll have to do an interpolation. You'll measure the distance, and between the two contours, what's the distance, and then what's the distance from the one contour to your manhole, and then that will help you to interpolate to determine what the level is.
Oh, okay, sir. Thank you.
Okay. Uh, any anybody else? Any other queries?
So for this uh, embankment conditions and trench conditions, what's the value for gamma?
Gamma is the unit weight of the soil. So that you would either from geotechnical conditions or you'd have to make an estimate. Unit weight of soil varies, could be anything from, if it's a very, very light soil, maybe 12 to 15 kilonewton per meter cube, usually around 16 to 18 kilonewton per meter cube, depending on the type of soil that you have there. So either in other words, it's the density of the soil, right? In simple terms, that's what the gamma is, the density of the soil. So either you'll send it to a lab for testing, you take an undisturbed sample and send it to a lab and they do it for you, or there are ways you can also determine that the undisturbed weight of the soil. Does that answer your question? In fact, just a follow up on when I talk of unit weight of the soil, not the sorry, I mentioned undisturbed. It's actually not the undisturbed unit weight of the soil. It's the unit weight of the backfill, unit weight of soil of the soil that you are backfilling. That is related to the backfill. So it's the unit weight of the backfill soil that you're placing back over there.
Thank you, sir.
Okay. Any other queries? Anybody else queries? Any question? Okay. If there's no further queries, we'll end the lecture at this point. And just a reminder again that the lecture on Wednesday will be on campus, where you will hand in your assignment. Right? You hand in on on no late assignments. So if I'll be there just for that lecture at the beginning of the lecture, and then I'll go to that. By the end of the lecture, I'm gone. If I don't receive it, well, then you'll get 0 for it.
Sir, sorry, I also have another question. Sir? Sir? Hi.
It's gone, eh?
Guys, cala ukubuza ukuthi the for i-assignment sengathi sephumile, or I don't know, lama spaces amancane kwi-layout niyawabala, like mase nibala ama-dwelling units, like those small spaces that you abangiphendulile nami.